All right. This is the first few slides. There are going to be stuff I've already gone over, and they were part of the midterm review packet, which I'm going to give to you, Victor, along with the final review packet. We're doing those first because they're Chem 1 topics that we should have probably, know from that time, but I'm sure you don't remember all of it. So I went over how to do these. You should remember how to do these. I've got some, you've done some examples of that. This one here in particular, let's talk about this one for a little bit. Both of those equations, you don't have to really write this down. You'll notice it's already on here. What I did was, before when I gave you these notes, I kind of just talked about them. I didn't actually have them printed out for you. Now they're printed out for you, which is nice. And I've got the equations right here. They're on your sheet. That same sheet that I gave you that's going to be given to you on the AP exam. Now, you actually don't get to use that sheet on every part of the AP exam. You only get to use it on the free response part. But either way, these calculations will be there. Now, if you don't remember how to do these, okay, I also had you copy these guys down for practice. And, they're really pretty simple because all you really have to do is look at these two equations, wavelength, frequency, H and C are given to you, and delta E is energy change. So you can figure that out. That should not be a problem. I'll tell you one problem as I was correcting these today that I've been seeing: forgetting units and forgetting to change units. This guy's in centimeters, and I've got guys like the wavelength is in meters, and this is in centimeters, and I've got to use speed of light is in meters. I've got to change centimeters to meters, so don't forget that. And the second one was the units. If I'm solving for a frequency, do you remember what the units of frequency are in? Hertz, right. Per second, okay? Waves per second. Okay, good enough. So that's a little summary. You're going to be doing that today, probably, if you haven't gotten to it. All of this we already went over. Remember doing these? Okay, went over all this. Victor, you're watching? Okay, don't try doing them now. Just watch, because I'm going to be doing the big review in a second. Look at here, for Victor's sake. Using the periodic table, and I actually, by the way, you can be flipping along. I have all these slides on there. You should be on this slide here now. Flipping along with your packet. Okay? You know what I did when I went over this before is I actually talked about how everything changed from bottom left to upper right. And the 4 things I have listed on your sheet, I actually typed them out and put them on there. I had you guys write them in on the packet when I was talking about it, but now it's right there. This is where you're going to have your highest electronegativity, your strongest, toughest ionization energies, right? Your lowest atomic size, because as you go across, it gets smaller, and your best non-metals, the guys who want to gain electrons. Down here, the exact opposite. And again, all of that was explained to you last time. I don't have time to do all of it. You should also be able to identify these trends in terms of a graph. Like that graph here would be of atomic size, and you can see that because when I'm going across a period, they're getting smaller. If I'm going down a group, they're getting bigger, and you should be able to read that. This is the opposite. This guy would be like electronegativity. And you should also be able to explain these exceptions. Those exceptions there, I talked about them and why they are exceptions. It has to do with the filled and half-filled sublevels and the different orbital shapes, the S and the P shape. So all of that was explained in the previous one. Now we're at the new stuff. Okay? Now, here, you're not going to find that one on here. You know where these 2 graphs are? These graphs are on the front page of your final review packet. So get that out as well. On the front page of your final review packet, I know you don't have one, and I'm going to give one to you, Victor, as well. Here, Vic, and Taylor.
Hey guys.
Here's another one. Alright. Now, I gotta tell you, full disclosure here, I'm a little confused. I'm a little confused about whether you're going to actually see this on the test or not. I actually found that in the 2014 revision, I was looking up the exclusion statements. I don't know if you've done that, Victor, when you were looking through your thing. But they basically said that one of the things that's excluded are phase change graphs. It says right on there, phase change graphs are beyond the scope of this course and the AP test. And then 5 seconds later, they also said that they're still important and you should know them from prior knowledge. So I'm not exactly sure. If you read the disclaimer above, it says some things like that are still considered prior knowledge, you have to know. They're just not going to be taught in the class. So I'm not really sure. But you should know what a phase change graph basically is showing anyway. Solid, liquid, and vapor, right? So this would be your boiling point. That would be your melting point, sublimation, triple point. And it's a graph of pressure versus temperature. You should understand what happens. As I lower the pressure, what happens to the boiling point? You should be able to predict that, right? It's going to get less. We did that in that vacuum pump over there. If I increase the pressure, like in a pressure cooker, it's going to cook at a higher temperature, and that's why the food cooks faster. If you're on top of a mountain where there's a lower pressure, food is going to cook slower. But it's going to reach the boiling point faster, won't it? It'll get to the boiling point faster because it's going to be at a lower boiling point. This graph also is of phase changes, but it's done a different way. Okay? Here I have, obviously, solid, liquid, and vapor. We've seen this many times in the past. Even this year we saw it a little bit. I referred to it. And we referred to it a couple of reasons. It had to do with entropy and energy. You can do calculations at the melting and boiling points if you know the heat of vaporization and the heat of fusion, and you know how much you have, the mass. Also, you can determine, using this equation, I want to talk about this because your sheet, and I'm pretty sure the sheet they're going to give you on the AP test, for the equation for this guy, doesn't look like this. It doesn't say delta H equals MC delta T, even though that was one I used all year, this year and last year. They prefer to say, oops, they don't prefer to say that. They prefer to say Q equals MC delta T. So you can write a little Q in for any one of these, too, if you will. You should know that that is the same equation. They generally tend to use Q when we're talking about physical changes like this, and we're calculating. We did calorimeter experiments and stuff like that. Those calorimetry experiments, they seem to me like they were using Q more often than delta H. Delta H is reserved most of the time for the ones we were doing in the back of the book. Enthalpy problems. Remember those? You looked up products minus reactants, that kind of stuff. All right, so don't be surprised. Oh, I never saw that equation before. You did. They're just calling delta H Q. Okay, it's the same equation. All right, but you all know what that is anyway, right? You all know that this is a phase change as well. It's diagramming and showing how there's no change in temperature at the phase changes, right? And that's why boiling water is 100 degrees. I can let the water boil for 20 minutes. It's still going to be 100 degrees. I can make it boil at a higher temperature. You know, changing the pressure, adding a solute to it would do it too. You know, but if once it's at a boiling point, it does not change until all of it changes. Hey, if I'm going this way, just a question here, real quick question. If I'm going this way, going from a liquid to a solid, is that an endothermic or an exothermic process? I'm getting half and half. It should be an obvious thing. Okay? Well, to go from a solid to a liquid, what do you have to do to a solid to make them turn into a liquid? You have to heat them up. You have to add energy. That's endothermic, correct? So going from a liquid to a solid, this is why it's always crazy, but turning it into ice, that doesn't give off heat. It feels cold, but it's giving off heat. That's the crazy part about this. And you may remember me doing I had the seed crystal in there. The whole thing froze. When it froze, I passed it around. How did it feel? It felt hot. Okay? So keep that in mind. Endo versus exothermic phase changes. Okay? All right. Now, let's get to the new stuff. This is new stuff. Turn your notes over to that. You won't have to take many notes here. I filled in I did more than I usually do. A lot of times I just give you the outline and you fill the rest in. I actually filled in all the words and even all the calculations and the formulas to save us some time. Even so, it's going to take me about 15 minutes to go over this because this is some tough stuff that we have not seen before. Okay? That's not true. When did we see this last? When did we see Chem 1? Yeah, we saw it way back in Chem 1, and for some of you that was 2 years ago, so I understand you probably don't remember it, and that's okay. We're going to go over it again. I'm going to go over it pretty fast, but it's all going to be there for you. All right, first of all, you should recognize what's happening in a half-life decomposition, a disintegration, I should say. Take a look. You might think to yourself that half-life means, and it is, the amount of time it takes for half of a sample to go away, right, to become not radioactive. So after one half-life, after one half-life, okay, and it won't go backwards, which is interesting. It won't do it until it finishes. Okay. After one half-life, you might think to yourself that, goes down from 80 down to 40. And then one more half-life from 40 down to 0, and I'm done. But of course, that's not what happens. You're always losing half. Put that away. You're always losing half. So from 80 to 40. 40 to 20. All right. And one half-life is 2 seconds there. Another half-life of 2 seconds, it goes down to 20. Another 2 second half-life, it's down to 10. And another it's down to 5. Okay? That makes sense?
But it'll never go to 0.
But it's, actually, you're right from a mathematical standpoint. It should only approach 0. But in reality, in chemistry, it would eventually get to 0 because In math, it never gets to 0 because why? Once you get to 1, what could you always do? You could do it to a fraction, 0.5, 0.25, and so on. In chemistry, once you get down to the last atom that's not radioactive anymore, and he goes away, he gives off his particle or whatever he's doing, that's it. There aren't any more. So you do eventually get to 0 in half-life decomposition. Okay. Everybody understands that. Now, I'm going to try to explain to you something that I hope you can use and I hope will be of use to you on the test. And here's why. It's a bit of a problem solving these things. The equation for them is not intuitive. It actually involves the rate law expression, and you would have to go through a lot of stuff to be able to derive it and then understand it. I'm going to show you a trick, an easier way to do it, one that I think makes sense, one that I could use one equation instead of using two separate ones. It's not what you'll find in the book. You will not find what I'm about to give you in the book. Oh, but before I almost forgot to give you this. Watch. There's another misconception about radioactive decay. A lot of people think, well, I get down to 0, if I was holding a chunk of uranium in my hand, and now it's no longer radioactive millions of years later, I'm holding nothing in my hand. It's all gone. But it's not true. It's going to look exactly the same. It's just that that particle is no longer radioactive. You're holding a chunk of something still in your hand. It just gave off its radiation. Okay? You understand that? It's not going to look a whole heck of a lot different. It's not like it was, I had a huge handful here, and now I've got half of a handful, and now I've got, a quarter of a handful. It doesn't work like that. Those particles are just no longer radioactive. But notice, I'm showing radioactive particles as black, and red particles as non-radioactive. There's the same number of particles there. They just gave off their radiation. Okay? That's kind of important to understand, too. All right, now let's get to the actual calculation. You don't have to write all this down because it's already in your notes. I already just explained to you what half-life is, okay? And there you have it. Now, the equation part is what I want to talk about. It's written down for you, and it's my own little creation. I got to tell you how I got it. All right, I guess my own creation. I got this guy because I thought of that previous problem, okay? I thought of that previous problem we were just doing with the decay, okay? And let's say we start with 80, like we started on that one. And I go through 4 half-lives. How much would be left? I go through 4 half-lives. For example, I start with 80. The half-life is 2 years, and I wait 8 years. So how many half-lives did I go through? 4, okay? So if I gave you that information, how much of the 80-gram sample would still be radioactive? I heard somebody say 5, which would be, it'd be basically half of 4, divided by 2 would be 40. Divided by 2, which would be 20. Divided by 2, which would be 10. And then divided by 2, which would be 5. And there's your final answer, right? So I knew what I had to get. Everybody agreed that 5 is going to be your answer. And you could do this in your head. But of course, what happens when you don't have easy numbers? What happens when it's not 80 divided by 2, 2 years divided by, into A equals 4 times? What do? You got to have an equation. And that's where I came up with this equation. Because will this equation work for this? Watch. 1/2 to X is the number of half-lives you have, right? How many half-lives will be on the go? 4. Equals the fraction remaining, A over A sub 0. A sub 0 is the original amount. That's the amount remaining. What was your A sub 0 then? 80, right? So it'd be 0.5 to the 4th power equals A over 80. Guess what? It works. Do it on a calculator if you don't believe me. It works. Guess what you get for A? 5. And this is the nice part about this. If I say the half-life is 1.37 years, and you wait 9.25 years, it'll still work. You just have to use a calculator, okay? It'll still work. You understand? All right, now, I'm going to go through those in a second. Let me show you why I'm not using the book one. The book equation looks like this, and it isn't by any means sufficient. That equation alone will not solve the 3 kind of problems you are most commonly asked for in half-life problems. You would also need that equation, okay? So you would have to use both, because you're solving for a K. You're solving for a rate law constant, which, of course, from a chemistry standpoint, makes sense, but is by no means intuitive, and it's, like I said, it takes about 2 pages to derive this from the rate law. You can see it if you want, so you can go through it in your notes. It is not given to you on the test. So I figured to myself, and I have been doing this all year. You don't realize this, but all year I've been trying to, and I will probably make even more concessions next year. Like the way I word things, the equations I give you, I often would have given you different ones. I just found one recently. I didn't realize that delta H with MC delta T was actually Q equals MC delta T. I told you to change that. Next year, I'll just teach it as Q, so that I don't have to worry about at the end of the year saying, oh, you know what, we were using it as delta H all year, really was Q. All right, I'll just teach it as Q because that's what the AP exam does. Well, this ain't on the AP exam. They don't give you this anyway. And it's more difficult to use. It requires 2 steps because you got to solve for a K. Notice K is in both. And it's kind of a pain. And by the way, I think that's intuitive, right? 1/2 raised to the power, however many half-lives, is going to equal the amount left, the fraction remaining. That makes sense to me. This, I don't think to anyone makes sense unless you go through all the rigmarole of going from rate lock expression, solving for K, and then doing all that. You can, and you'll have to, perhaps in college, I'm sure. But I think you're going to probably get a problem like this in the AP exam that would be more like one of the multiple choice questions. Kind of like that 80, 2 years, 8 years kind of problem, right? That kind of problem, more easily solved by this method because it also doesn't require you to solve 2 separate equations. All right, let me just go through the rest of this then. These are all on your notes already. That's why I did this. That's the first example, and I even did it for you. Let's go through it quickly. Let's read with this question. Isn't this the exact same question I was giving you a minute ago? Exact same question, right? So I just went through it. There's your equation. You have to first find how many half-lives you undergo. And by the way, on the review packet, you have 3 questions on half-lives. This is one of them, okay? Although it won't be the same numbers. How many half-lives you figure out by just how long you waited versus how long a half-life is. That's 4 half-lives. Great. So now I know there are 4 half-lives. So I can plug it into the equation. 1/2 to the x equals a over a sub 0. So 1/2 to the 4th power is going to equal a over 80. Does everybody see where that 80 came from? Here's the original amount. That's what a sub 0 means, original amount. A is the part I don't know, and then solve it, and there it is. A equals 5 grams. Got it? All right. So it's been a long time since we did those guys. Hey, that's not the only way I can ask it. I can ask it this way, too. This is called radiocarbon dating or carbon-14 dating. You've heard of this, I'm sure. I talked about it last year. We did problem time. I know, or 2 years ago, if you had me 2 years ago. So, let's look at what happens in this one. Okay, follow me. I know it's also written down there. You realize a over a sub 0 is another way of saying the fraction remaining, right? 0.636 times the activity, all right, it has today that it used to have. Let me ask you this. If it had half the activity, it's a simple question, and a kind of question you might get in the multiple choice format. If I rewrite this the same question, piece of wood today, carbon-14 dating, has an activity that's half of what it used to be. The half-life of carbon-14 is 5730. How old is a piece of wood? 5,730 years. You see? Okay? Well, this guy's got 0.636 times the activity it had. Or it has it today's. Oh, and by the way, I know I explained this back in the day. You probably don't remember it. The reason carbon-14 dating works is this. When a living thing like a tree dies, it's no longer incorporating carbon into its structure. It falls over, it's buried in the ground, and 1,000 years later we dig it up. We want to know how old it is? You can compare the carbon-14, because when it was dead, it no longer took in any new carbon-14. The carbon-14 that was in there started to decay. Yes, carbon exists as 3 isotopes. Carbon-12, carbon-13, and carbon-14. Carbon-14 is radioactive. So the carbon-14 that's radioactive started to decay 1,000, 2,000 years ago. How much of it's left compared to today tells me how old the tree is. Okay? Or how old the tree, or the piece of paper, or whatever it is I'm trying to do. Okay? All right. How do we do this problem? Well, remember, this fraction is telling you that's the a over a sub 0. That's what that is. That's the fraction. It's 0.636. So the problem simply becomes 1/2 to the x equals 0.636. See it? So how do you solve that? I realized I didn't do a good job of this in the last period. Somebody was asking me this later. Watch this. And if you don't believe me, you have to try it yourself. Again, I thought of this, the easiest way to explain these kind of problems. Why do they even have an ln in that previous equation? Because the only way to solve for an exponent, like say I have 2 to the x equals 8. We all know the answer to that. What is it? Everybody agree it's 3? 2 times 2 is 4 times 2 is 8. We all know it's 3. How would you solve it if it was like 1.75 to the x equals 0.394? That was my question. So I decided, well, how can I do this? Well, it turns out all you have to do is take either the log or the natural log of both sides. Because what's the log or natural log of 2 to the x? It's the log of 2 times x, right? So it'd be like, I think it's 0.301 or whatever times x equals blah, blah, blah times, it would just be the log of that, whatever that is, 0.47, whatever. I actually have this one worked out so you'll see it. So that's the reason you're taking the log. The log solves for the exponent. It takes the exponent out of the exponent and brings it down. So what it looks like is this. The natural log of 1/2 to the x equals a natural log of 0.636. So if you type into your calculator 0.5, the natural log of 0.5, you get negative 0.693. You type in natural log of 0.636, you get negative 0.453. X, that's easy, right? What does x equal, right? Divide them. Everybody see what I did there? X equals 0.654. Now you say, well, that's not my answer. No, it's not, but it pretty much is telling me what my answer is going to be. It says my half-life is 5,730 years. I know it went through that many half-lives. Not even a whole half-life. So I simply, did I get that or not? I have to simply multiply it by the half-life. And that tells me that that piece of wood is 3,750 years old. Okay? Hasn't even gone through one half-life. Okay, it's gone through 0.6.
So the side on the left is always going to be negative 0.6.
Well, again, the sign on the, well, yeah, it's a good point. It's a very good point. Who's been working with natural logs? Have you seen 0.693 a lot? Yeah, because it is a natural log of 0.5 or 1/2. Okay? So you're right. That actually shows up in the equation. If you were to look at my prior problem, it actually had that in the equation. Take a look. Let's go back to that one. That's kind of neat that you said that. Let's look at that equation again. The one that's from the book. Okay? There it is. Okay, that same number. And what's great, also you notice something about it. Notice mine was negative on both sides, so it crosses out and it becomes a positive. Why is their equation ln of a sub 0 over a? So you don't get a negative. Exactly. Mine was a over a sub 0. But the problem with this is you have to solve each of them for that problem. Whereas I have one equation you only have to solve, and it's a more intuitive equation. Now, I'm sure people watching this on YouTube, if there are other chemistry teachers, say, he's such a jerk. What's he making him do that for? You know, the right way to do it is this way. This may be the right way, and it certainly isn't impossible for you to understand. Okay? But I feel that this is a better way. I mean, I've looked at it for a long time, and I don't see how this is more intuitive or faster than this. I think this is a better way to do it. Just my opinion. Okay. Now, we're almost... We have one more of these to do.
Camel work.
Yeah, right.
Chem teacher.
One other way I can ask a question on these. Watch. I can also ask, okay, I give you how long this guy's been sitting around. And by the way, this is the kind of question, I think I should give a little bit of the background here. Where would we use radiocarbon dating and trying to get how old the Shroud of Turin is, or how old the parchment paper is from the biblical times or whatever? I could do that with carbon-14 dating. This is a modern use. All right, there's a whole branch of medicine called nuclear medicine, okay, where they inject different isotopes into your body so they can track them through your body. There's also isotopes that are injected to kill cancer. They're injected, they're called seeds. They're put next to the tumor, and they kill the tumor. The thing is, you got to know, when you're the person putting these things into somebody, you got to know how much radiation is being given off for how long you're going to be radioactive. I've had students in the past, when we took a field trip up to the power plant, who had a radioactive dye in a CAT scan or something. He could not go in the power plant. Anybody know why? He could be sitting in class right here. It wasn't because of a safety reason. I mean, he could sit in class. It would set off the alarms. Now you say, well, so what? If they know he's radioactive, no big deal. He couldn't get out of the plant. If you go into the plant, Every person who leaves the nuclear power plant has to walk through a detector. If you set off the detector, they send you back. You brush your clothes down, you go through again. If that didn't work, they send you back. They strip you down. They put on scrubs and you send you through there. If that doesn't work, you take a shower. You do everything you can until you can walk through there. I don't care how many showers that guy takes. If he's got it in his body, he's never going to get out of the plant because he'll always be setting off the alarm. You say, well, we know it's because of this. No, you don't. He might have stepped into something, might have picked up a particle that's radioactive on his clothes. That's why you first check the clothes, then you check the body. You know, you check all these different things. You can't get out of that plant unless you're not radioactive. All right? Because otherwise you'll go home, you're playing with your kids or your dog, and you're going to give your dog or kid cancer because you've got all these particles on you. I mean, that's the theory behind it anyway. All right, so this is a good example of how if I was injecting someone with this dye, I'd have to say, okay, you can't sleep with your wife for the next 5 days or 2 weeks or a month because you're going to be radioactive. You need to sleep in separate beds. And that actually happens. All right, if you're giving someone these seeds or different other isotopes that are radioactive for a certain period of time, you aren't allowed to be around other people. You're not allowed to hold your grandchild on your lap, you know, while you have these things. So here's a good question on this one. I have an isotope. It has a half-life of 40 minutes, okay? And it has this many curies it's given off. What will its activity be 2 hours later? Well, what do we have to figure out? We got to figure out how many half-lives he underwent, correct? So how you get that? Half-lives would be 120 divided by 40. Why 120? 2 hours, right? 2 hours is 120 minutes divided by 4. Gives you 3 half-lives. Everybody agree? 3 half-lives. 1/2 to the x equals a over a sub 0. 1/2 to the 3, that's how many half-lives, equals a over a sub 0, which is the fraction remaining. 0.125. That's what a over a sub 0 would equal. So you got 0.125, the activity of that 4.181 curies. You now have 0.601 curies of radiation being given off. Now, they can also look that up and see, when is that no longer dangerous? How long would you have to wait till you could, you know, be around other people or whatever? Okay? All right. Now, the last thing is the types of radiation we're going to go through. That's also in your books or your paper, so turn to that. All right, the types of radiation. You should recognize a lot of these terms. We haven't done them in, like I said, a year or two. So a lot of you want to go over these quickly. They're right there for you to do the review packet with me. Alpha, beta, positrons, gamma, okay? Let me go over real quickly what each of these is for the description. The alpha particle is just a helium nucleus, okay? Helium nucleus, 4, 2 means it has how many protons and how many neutrons? 2 protons, 2 neutrons. Not 2 protons and 4 neutrons. I hate when people do that. 2 protons, 2 neutrons. Okay. A beta particle is an electron. Say, oh, wow, electrons? I didn't know they were radioactive. Electrons, that's ejected from the nucleus. Why would the nucleus doesn't have electrons in it? There's protons and neutrons in there. Yeah, actually there are. Those electrons are given off when you convert. You should need to write this part down here. When a neutron is converted into a proton. When a neutron is converted into a proton, it does give off an electron. Okay? And hence, the charge, how a proton becomes positive. A positron is basically a positively charged electron, and that's given off when a proton is converted into a neutron, which can also happen as a form of radiation. And you need to write that down. Gamma rays, if you see them in an equation, you don't have to worry. They have 0. Matter of fact, sometimes you'll even see gamma written like this. Okay, you'll see gamma written when it's 0 over 0. No mass. Okay? And by the way, there should be there's no 1 there. I think yours looks that way. Is that yours correct like that? I accidentally, when I shifted this over, I got the 1 out of spot. Okay? Gamma rays are just energy, no particular mass. Neutrons, 0 charge. That's a 1 over a 0. No protons, 1 neutron. And a proton will be a 1 over a 1, which I had there a second ago. Okay? Now, the nice part about these equations are, I'll get to the equations in a second. The other question in the review packet, and something you should also understand, is something called mass deficiency and nuclear binding energy. Let's talk about that a little bit. If I give you these masses for a proton, neutron, and electron, and I tell you you have nitrogen 14, okay? And I say, what is his theoretical mass should be for nitrogen-14? Well, you would take how many protons? That guy times 7. Everybody agree? Because that's his atomic number. How many neutrons? 7. And how many electrons? So I would multiply each of these numbers by 7, and I would add them up. You know what you'd find when you added them up? They don't equal the actual mass of the nitrogen atom. Okay? The deficiency between that is called the mass that you would subtract those two numbers. That mass that's missing is what's responsible for the nuclear binding energy. That's what's actually holding the nucleus together. Okay? How do you calculate that energy? E equals mc squared. You say to yourself, it's going to, right away, when you subtract those two numbers, the summed mass and the actual mass, it's going to be some really small number, like 0.314 grams per mole. Really, really small number. But it's a lot of energy. Because what are you multiplying him by? Speed of light squared. So that's a huge amount of energy, believe it or not. Okay? All right. So you have to do one problem like that in the review packet. And finally, you have a lot of these. Okay? So let's just go through. I'm not going to do every one of these. I'm going to do like the first couple here, and then I'm done. Finally. I told you it would be a long class, but you're going to have time to get the rest of the whole next period. You're going to be working on these packets. All right, let's take a look here. These are really easy. All you have to do is sum up on either side the numerators and the denominators. I hope you're not just doing that. I hope you realize that the denominators are the number of protons, correct? So 2 here, I must have how many here? 92. 4 here, I must have how much there? 238. You see why? And you can fill this one in because you've got to fill the rest of them in anyway. Now, how do I know what element that is? I look up 92, who happens to be, I hope you even remember that guy, uranium. Right. Okay. If I ask for the type of particle, what type of particle do I want here?
Alpha.
Yes, this was an alpha particle that was given off. I will put alpha or that. That's the symbol for an alpha. And it's also Jesus. Actually, it's just that. It is. Bumper stickers? You ever see it? Anyway. Now, do be careful when you have negatives. A lot of times people do this backwards. 16 and a minus 1 is what? 15. Up there, 32. What element is over here? Phosphorus. Good. What particle is given off there?
Beta.
A beta, which can be symbolized with a B or an E with a minus 1. B minus 1. Okay? Okay. Over here, let's do this last one I'm going to do. You can do the rest of them yourself. 103 and 0. Well, 98 over here. What does that mean? I need 5. Good. Be careful. I've got a 3 in front of here. Just like any other coefficient, I distribute it. 3 times 1 is 3. 3 and 259 is how much? I'm not subtracting. I'm adding. How much is that? 262. What do I need up there? Everybody agree it's 10? So what is that thing?
Boron.
That's boron. You stupid boron. And that's not the particle. You say, well, I can't put boron for a particle. No. I'm asking what particle was given off, or accepted. In the case of this guy, it's going to be accepted. It's going to be a neutron. Right.
Jimmy Neutron.
Jimmy Neutron. I used him, by the way, when I did the notes. Okay. A couple of changes on your review packet. Go open up the final review packet, last page. On the nuclear stuff. Stuff on the nuclear there. Cross out the stuff about above or below band. I don't think they're going to ask you that. Hopefully they're not. See the column that says above and below band on the nuclear, on the review packet, final review package.
I remember that.
I was trying to figure.
I was terrible at it.
Anthony was the best in this chapter.
What's that?
Anthony was the best in this
Really? You like this stuff?
chapter. You knew how to do it.
Wow. How come?
Just if I understood that.
Okay, well, good. Then that's good. Cross out the column that says above or below, but also cross out the nuclear reactor stuff underneath that. That's definitely not going to be on the AP exam. Moderators and stuff like
That was
that.
just for your fun.
That was for fun, and it was fun.
Oh,
I hated that chapter.
I'm glad.
The very